All right, so let's go through this here, guys. First one here, we've got sodium with phosphorus, so that is an ionic compound, thus it is named sodium phosphide. No capital letters. Okay, and our second one, we've got silicone with bromine. That's molecular. There's only one silicone, so it's just silicone dibromide. Again, no capital letters. Okay, give the formula for the following compounds. Copper 2 nitrate. So we know copper is Cu, and the Roman numeral tells us it's the 2+ kind. All right, nitrate is NO3, and it has a -1 charge. So when we drop and swap, the 1 goes on the copper, and the 2 goes outside of a set of brackets on the nitrate. So CuNO3 bracket 2. And for number 4, diselenium triacetatide. Se2AT3. Okay. Questions on those ones? All right. Indicate whether the following compounds are soluble. Silver chloride. Pretty sure that's not, but we'll double check. Okay, so chlorine is right here, soluble with most things. Silver in the not so soluble row. All right, so that one would be insoluble. Okay, calcium iodides. Okay, iodine's in that same row, soluble with most, but okay, calcium is not in that list there, so it is included under most, which means it is soluble. Okay, copper nitrate. We said all nitrate compounds are soluble. Okay, and chromium sulfide. All right, so sulfide is right here, soluble with all of these things. Chromium is not among that list, therefore that is insoluble. All right, so 1 mark for each of those. And then identify the type of reaction that is occurring. All right, we've got an ionic compound reacting with an element to form a new ionic compound and a different element. What kind of reaction is that, Stephen? Single replacement. 1 mark for single replacement. Okay, and on the bottom one there, we've got an element reacting with an element to form a compound. What would that be? Synthesis. Okay, so it's out of 10. Give them a mark out of 10. Let them see it. Then please put it in the box and back to your desks. Okay, now we've talked about balancing. Okay, we're just going to quickly review balancing, and then we're going to talk about, okay, the process of predicting the products of a chemical reaction, which really is not very difficult. All right, every one of the reactions we have gone over looks different just from the reactant side. All right, for example, synthesis. The reactants in a synthesis reaction are 2 elements. Okay, the reactants or reactant in a decomposition reaction is a single compound. It's the only reaction that starts that way. Okay, a combustion reaction. Its reactants are unique in that it's the only reaction we've gone over that would have a hydrocarbon and oxygen as the reactants. Okay, for a single replacement reaction, the reactants are always 1 ionic compound and 1 element. All right, and for a double replacement reaction, it's the only kind of reaction that starts with 2 ionic compounds. So we can tell what kind of reaction is going on without even seeing the products. Okay, we can tell just by looking at the reactants, right? And that's kind of where we need to go today, is be able to recognize what kind of reaction is going on and then know this is what happens in that kind of reaction and be able to tell someone, here's what the products are going to be. All right, now for a combustion reaction, that's easy. The products are always the same for a combustion reaction. They're always what? CO2 and water, always. Okay, always CO2 and water. So that's just one you can just remember. Okay, you never have to think for that one. All right. For the others, you'd have to look. What were the reactants? How are they going to go together? Are they going to make an ionic compound? Are they going to make a molecular compound? Most of the time, it will be ionic. Okay. Or if it's a double replacement reaction, what will the 2 ionic compounds be? Okay. In a single replacement reaction, which element's going to be left by itself? Things like that. Okay. Again, not difficult decisions, not difficult things to think up. Okay, just new. All right, so the point of balancing here, so key points for balancing is that we got to understand the amount of atoms on the reactant side of an equation must be the same as on the product side. That's the law of conservation of mass. We have to obey that. Okay. Learn to use coefficients to balance equations. Remember that coefficients are those big numbers that we put at the beginning, okay, or in front of compounds in a reaction to make them balance, okay? And understand that matter cannot be created or destroyed. Okay, so law of conservation of mass, and this is very often a multiple choice question. Okay, is which law is this statement? And then I give you this: mass must always be conserved, or matter cannot be created or destroyed. And then it would have 4 options, one of them being the law of conservation of mass. Okay, so it must always be conserved in reactions because matter cannot be created and it cannot be destroyed. Since all matter has mass, the mass of the reactants must equal the mass of the products. What if in a reaction a gas is produced? Are you still going to have the same amount of mass on both sides? Yes, as long as you capture the gas. Okay? If you don't capture the gas, it will go out into the room, and then it will appear as though you have somehow destroyed matter on the scale. All right? And that's where people sometimes make a mistake, is, you know, they're doing a reaction and it's not in a sealed container. Right? And then as a result, a gas escapes, and their final products have less mass than their initial reactants did. It's not true, it's just they didn't collect all the gas. Problem, of course, with doing a reaction in a sealed container is what? Oh. Okay, well, oxygen might get at it, but we might want that. Right? If it's a combustion reaction, we might want that to happen. Okay, if it's a combustion reaction, you're right, it's going to end when all the oxygen is used up, but that might be what I want, okay? Usually in a reaction, you kind of have a limiting factor, okay, so that the reaction stops at some point. You run out of reactants. Right, pressure. Okay, gases tend to take up more space than their liquid counterparts do, right? And especially if that reaction is also exothermic, which means it gets hot, because gases, when they get hot, take up even more space, which creates more pressure. All right? If they can't take up more space, that is, they're in a fixed size container, then they exert pressure on the inside of that vessel, and that could lead to a rupture, all right? And that's dangerous. So you'd have to make sure you were doing this in a sealed container that could deal with expanding gases and their resulting pressure. All right, so that's kind of an important thing to think about. All right, so in this reaction here, I've got 2 hydrogen molecules. Okay, 2 hydrogen molecules containing how many hydrogen atoms? 2 each, so a total of 4. Okay, reacting with 1 oxygen molecule containing how many oxygen atoms? 2. All right, because remember, we're balancing this by atoms, not by molecules, right? Okay, we're looking here. Our products are water, 2 molecules of water containing 1, 2, 3, 4. Okay, atoms of hydrogen and 1, 2 atoms of oxygen. Is it balanced? Yep, everything that was on the reactant side is on the product side, right? So that's the purpose of doing that. And of course, it is important to recognize the difference between a molecule and a single atom. All right, remember that we always balance by atoms, okay? Unless, of course, it's a complex ion. Then we can treat it all as one piece, okay? All right, so this is simply, okay, the law of conservation of mass restated, right? You might just want to underline that or highlight that, because again, I said that's usually a multiple choice item. Okay, there's usually a few questions to do with the law of conservation of mass, because it's kind of important. Okay. All right, in this diagram here, right, these are our reactants. So box A here is the reactants for this reaction. Which one of the boxes shows the correct products? Peter? Box D. All right. Now, we can say that not having any idea what those little balls represent. Okay? It's just a reaction. The only reason I know that D has to be the correct products is because it's the only box in which the law of conservation of mass has been obeyed. All right? There are 7 little yellow atoms. And in box D, that's the only, sorry, 8 little box, little blue, white, yellow atoms. Okay, box D is the only box that actually has 8 of them still in it. Okay, C and D have less than 7. All right, and that isn't even really looking at the at the red ones, okay? In this one here, there's 2, 4, 6, 8, 10, all right? 2, 4, 6, 8, 10, all right? So it's conserved. Now, does it matter that these two little yellow atoms didn't do anything? Nope. That happens in a reaction. You usually have more of one reactant than another, okay? And so some of the reactants don't get used. That's fine, okay? The ones that do participate in the reaction, they react, they form new compounds, and you have some left over. Okay, that's fine. It still contributes to the overall mass of the reaction. All right, questions on that? All right, when you're balancing, and we've kind of gone over these steps, but now at least you have them kind of in a written form, okay? In step 1, you write the chemical formula for each reactant and product, and you don't have to include the state of matter. We'll cross that right off, okay? We don't include the state of matter anymore, okay? We used to, but we don't now. Why is it important to do this when you have the formulas and not the written form of the reaction? Can you even balance the written form of a reaction? You can't, because ionic compounds, I mean, and you don't have any numbers essentially in the written form, so you can't balance the written form of a reaction. It has to be in formula form. All right, step 2, try balancing the atom or ion present in the greatest number. All right, that's what we've always said to do, unless that atom is what? Oxygen. Okay, so that would be the exception. Okay, we might just want to write in there oxygen last. Okay, and we use coefficients. That's the big numbers in front of an element or compound to get equal numbers of atoms on both sides. What does the coefficient mean? If I put a big 2 in front of NaCl, what does it mean? Larissa, what does it mean? Right, that there are, if it's NaCl, 2 molecules of sodium chloride. If I put that in front of magnesium, it means there's 2 atoms of magnesium. All right, the 2 always means multiply whatever's behind me, be it compound or element, by 2 or by whatever the number is. Okay. Step 3, repeat step 2 to balance each of the remaining atoms or ions. So what I typically do is I balance that thing that's present in the largest number, and then whatever it was attached to, I balance next, because my number has probably thrown it off. Whatever coefficient I put in has probably put the thing it was attached to out of balance, so I'll balance it, and then so on and so on, back and forth from reactants to products, okay, until it's all done. All right, lastly, check the final equation to ensure all atoms and ions are balanced. A lot of times people will just stop when they've filled in all the blanks. Sometimes you will find that your last number doesn't completely balance the equation. It actually throws something off. If that's the case, you've probably swapped and dropped something incorrectly along the way. All right, but it is always worthwhile to check and just make sure. All right. If, on an exam, I gave you a question that looked like this. Run out of room here. And I said, balance this reaction. What would you have to do? Philip? Okay, that's the answer I don't want to hear, though. Yeah, you're right, it's already balanced. But don't do nothing. This is a fill-in-the-blank question. If you don't fill in the blanks, what do I assume? Yeah, put ones, because if you leave it blank, I have to assume you didn't know how to do it. Okay, so if it's a fill-in-the-blank balancing question, please fill in the blanks. All right, so that I know you knew it was already balanced. Show me what you know. Okay, don't take for granted. I can't make assumptions on when I'm marking questions. Okay, so if it's a fill in the blank, put ones in. Right, and if you've got other numbers and one is supposed to be a 1, don't leave that blank, because again, I can only assume a blank means you didn't know what to put there. Right, so always put a 1 in when you're balancing your reactions, especially on a fill in the blank kind of question. Okay, everybody with me there? Yeah. What number should never appear in one of those blanks? 0. If you put a 0 there, you're saying my coefficient is 0. Anything multiplied by 0 is 0, which means you have none of that, and that is impossible. All right, so make sure that 0 never appears there, because I do see that. Okay, people think that by putting a 0 there, it means 1. No, 0 means nothing. Okay, 1 means 1. Put a 1 there. All right. Okay. So example here, we've got this reaction. Copper solid reacts with silver nitrate that is aqueous or dissolved in water to produce solid silver and a solution of aqueous copper nitrate, copper 2 nitrate in this case. All right? Now it says oxygen atoms are present in the largest number. Thankfully, those oxygen atoms are part of what ion? Nitrate. Can we balance nitrate all as 1? Yes, we can. All right, so that's what we're going to do. Okay, nitrate is present as a 2 on this side, but present as a 1 over here. So I would need to put a 2 in front of silver nitrate, as they've shown here. When I do that, it balances my nitrates, but throws out the silver. So by having a 2 here, I would also need to write a 2 here, right? And so that's what we see in the next step. Now I've balanced the silvers, the nitrates are also balanced. Now I need to look at copper. There's 1 over here, 1 over here. It's already balanced, okay? We would say we do want to write the 1s, okay? If it was a fill in the blank. If you were just doing a worksheet or something like that, okay, leaving it blank would be fine. But again, fill in the blank, make sure you put 1s in there. All right. And remember here that polyatomic ions are balanced as a single unit, not as individual atoms. All right? The only time you would balance them as individual atoms would be if they broke up. All right? And you've had a few on your worksheets, like when you had carbonate in one of them and it broke up into 1 oxygen atom attached to something else and 2 oxygen atoms attached. I think it was something like this. CaCO3, and it broke down into CaO and CO2. Okay, something like that. You guys with me there? Right? In a decomposition reaction like that, okay, and this is a decomposition reaction, it's one thing breaking down into 2 things. They just weren't elements. We said that could happen once in a while. Okay, now obviously I can't balance carbonate as a single unit. All right, because it doesn't stay a single unit over here. All right, everything is balanced, so all I have to do is write 1s. All right, there's 3 oxygens over here. 1 plus 2 is 3 over here. 1 carbon, 1 carbon, 1 calcium, 1 calcium. It ends up being fairly easy because it was already balanced, but we have to make sure if an ion breaks up that we balance it separately. Okay, predicting. First step to predicting the products of a reaction is to identify what kind of reaction is going on. All right? Once we know what kind of reaction is going on, we have a pretty good idea of what's going to happen. All right? So I want you to write down these 4 examples here, and we're going to go through the prediction process with these. Okay, so like we said, the first step in predicting the products of a reaction is to identify what type of reaction is going on. All right, so let's look at number 1 here. In number 1, I have an element reacting with another element. What's the only kind of reaction that starts with 2 elements? Hannah? Synthesis. All right, in a synthesis reaction, what are these 2 elements going to do? They're going to combine. They're going to form a compound. All right, now, if they're going to form a compound, I got to look at what kind of compound are they going to form. Well, this is a metal, and this is a non-metal. So what kind of compound are they going to form? Ionic. All right. In an ionic compound, which one should I write first? Metal. See, now here's where all those little rules that you just took for granted start to come into play. Because I've done this to people on a test. I've switched the order. I've said O2 plus Ca arrow. And you know how many people do this? A lot. Okay, because they forget that simple rule that says an ionic compound is metal first, non-metal second. Okay, so we don't want to get caught on something silly like that because Coderre is mean and he'll do things like that to you. Okay, all right. Ca is going to go with O. All right. What I should probably check now, since this is an ionic compound, is did I swap and drop that correctly? Because if I didn't, I'll never be able to balance the reaction. All right, oxygen's a -2, calcium's a +2. Yes, I did swap and drop that one correctly. Okay, what's my last step? Balance the reaction. It's the only thing that hasn't been done yet. All right, present in the largest number. Calcium's already balanced. Oxygen, now I have to do it. Okay, I'm doing it last, but it's present in the largest number. Okay, I'm going to put a 2 here, which gives me 2 oxygens on each side, and now I have a 2 here, 2 calciums on each side. Okay, was that very hard? Oh, you may. Okay, does that sort of make sense? All right, we can identify all of these just from the reactants. All right, let's look at number 2. My only reactant is magnesium sulfide. It's the only kind of reaction we went over. Decomposition. Decomposition is the only reaction type that starts with only one reactant. Okay, in a decomposition reaction, this has to break down into its 2 parts. Okay, so I know I'm going to have Mg and I'm going to have S. Here's something I have to check for, though. Are any of these special? The sulfur. The sulfur is the most special of the special elements. It comes in sets of 8. Okay, that's an important thing for us to check. If we don't do that, okay, yeah, we'll get a mark for predicting the products correctly, okay, but after that we won't get any balancing or anything like that. All right, so now that I've done that, now I can look to, there's no compounds, there's nothing to swap and drop, now I can look to balance the whole reaction. I've got 8 sulfur over here. What do I need to put here? 8. Okay, how many magnesium does that give me? 8. Okay, and now I'm balanced. Okay, I could also put a 1 here if I wanted to. Everybody okay with that one? All right. Number 3, I've got carbon and hydrogen together in a compound reacting with oxygen. Only reaction type that starts that way, Donna? What kind of reaction starts with carbon and hydrogen reacting with oxygen? Take a guess. Combustion. Okay. What are always the products of a combustion reaction? CO2 and water. Okay, so this isn't one where you try and figure them out. This is one you just memorize. Okay, products of a combustion reaction are always CO2 and water. Now, do we have some special rules for balancing combustion reactions? We have 2 special rules. The first rule is to balance them alphabetically. And the second rule is the rule of 2, which is if there's an even number of carbons, we start balancing with a 2. Is there an even number of carbons here? All right, so that rule is moot. We're not going to use it. All right, 3 carbons starting alphabetically. 3 carbons over here. 8 hydrogens. 8 hydrogens over there. All right, now I got to balance my oxygens. 3 times 2 is 6, plus 4 more is 10. 5 times 2 is 10. Okay, everybody all right with that one? Okay, so for combustion, like I said, you basically just don't memorize it. Okay, we just did this one a minute ago, was the example I did. Let's try a different one. All right, my reactants are 2 ionic compounds. Sierra, only kind of reaction that starts with 2 ionic compounds. Double replacement. Okay, what do we always say happens in a double replacement reaction? Who do we switch? Switch the... Yeah, it doesn't really matter. I always just say switch the metals. You could switch the non-metals too. But if I do that, will that give me 2 different ionic compounds? Is that going to... That's what I want, right? Okay, the biggest mistake I see here is people not following that rule. They put 2 metals together, they put 2 non-metals together. All right, is that going to happen? Because it doesn't produce 2 ionic compounds, right? And in reactions, in replacement reactions, you can only have ionic compounds. All right, so on this side then, H ends up with OH. Okay, and K ends up with SO4. Now, they're both ionic, so what do I need to do with both of them? Drop and swap. Yeah, I have to balance the products, okay, and then balance the reaction after. I don't want to use balance twice, so we'll say drop and swap both of these. I haven't. Okay, I'm going to balance when I balance the reaction, I'll make sure I have two hydrogens on both sides. But for right now, this is a -1 and this is a +1. So that's correctly balanced the way I've written it, right? Or correctly dropped and swapped. All right, and over here, this is a -2 and this is a +1, so I'm going to have K2 SO4 for that compound. Now I've swapped and dropped. Now I want to go back and balance the whole reaction. All right, present in the largest number could be hydrogen or potassium. Doesn't really matter, okay? And as Aiden was saying here, what happened to that 2? Well, here's what happened to it. I'm putting it in now, okay? Now there are 2 hydrogens, okay, on both sides. But now there are 2 hydroxides over here and only 1 over here. So what needs to go in front of the KOH? 2. And lo and behold, that makes my potassium balance on this side, and sulfate is a 1 on both sides. Okay? Everybody with me there? All right, there's one reaction type we haven't done. I'm going to put one up here, and I want you guys to try it on your own. Okay, I'll give you a minute or two to try that one. Okay, single replacement are probably the toughest ones, oddly enough. Okay, in a single replacement reaction, okay, what am I going to get as products in general? I have to get what kind of a compound? An ionic compound and then an element, right? Now, what I need to make sure of is that I switch the right things. Right now, magnesium, well, not right now, always, magnesium is a metal, okay, but it's by itself right now. And then I've got this ionic compound that has cesium and it has nitrogen in it. So if I want to have an ionic compound on the other side, which 2 things are trading places? Right. I got to change the things that are alike. Okay, which means I had a metal by itself on the reactant side. I'm going to have a metal by itself on the product side. If this was a non-metal, then I would have a non-metal by itself on the other side. Okay, so I know cesium ends up by itself, and I know then that magnesium must become part of a compound with nitrogen. All right. Now I need to check: is cesium a special element? No, it's a metal. Okay, the only special metal is hydrogen. So, okay, we don't have to worry about putting any little numbers on cesium. It's just going to be a single by itself. Then this is an ionic compound. What do I need to do with it? I need to drop and swap. Nitrogen's a -3. Magnesium is a +2. So that's going to be Mg3N2. All right, now I've swapped and dropped everything correctly. Now I need to go back and look at balancing. Okay, on this side here, I've got 3 magnesiums, okay, present in kind of a large number. All right, need to go over here and make sure I have 3 magnesiums. All right, so now that's balanced. Over here, I've got how many nitrogen? 2. How many here? 1. If I put a 2 here, am I going to run into problems? Not really. How many cesium does that give me? Okay, so 3, 2, 6, and 1. All right, is that making sense? All right, so really it's not a whole lot different than what you've been doing. Okay, predicting the products is pretty straightforward. Like if we know reaction types, we know what's supposed to happen on the other side. Ellie. It makes no difference whatsoever. Yeah, the compound could come first and then the element by itself. That part doesn't matter, okay? All that matters is that in your ionic compound, the metal came first. Yeah, okay? Any other questions on that? All right, so we're going to practice that for a while here, because we got to be able to do that in order to do the lab, because we got to be able to predict the products of our reactions for that. Hey, guys, good question just came up here, and just want to address it, because I do often see this is actually a very common mistake that people make. In number 5 here, we had a single replacement reaction. I'll oftentimes see someone do this in order to balance the reaction. Okay, and while the numbers balance, why is that not right? Right. This little 3 means 3 magnesium atoms as part of a molecule, or 1 molecule of magnesium. Well, magnesium doesn't make molecules with itself. Okay? Magnesium exists as separate metals. The only time something gets one of those little numbers is if it's one of the special elements. Okay? Only the special elements get little numbers when they're by themselves. Okay? There aren't any special metals other than hydrogen. Okay? So they all get big numbers in order to balance. Right? Important to know the difference there. Which number is that, Andres? 11. Okay. I don't have that file up right now. Okay, can you just give me the reaction there? Okay, gives copper 2 sulfide, and okay, so actually the rule I told you doesn't apply here. Okay, gives gives copper sulfide, right? Copper 2 sulfide is what it says. Okay, so the way I can tell, sometimes in a question, if you just get a reaction like this, it doesn't tell you which charge specifically is on one of these multivalent metals, but can I figure it out? Like if chromium is in a compound here with sulfide, which it is, right? I can figure out that this is chromium with the 2+ charge because sulfur is always -2, right? And so over here it would have the same one. And in the reaction there, it told us, okay, that it was copper 2 sulfide on the other side, right? Okay, but sometimes you are going to run into a question where they don't tell you, okay? And you're going to have to figure it out. Well, if they don't tell you and there's no compound over here for you to use to figure it out, you go with the most common charge, which is the first one listed in the box. All right? So if they go, let's say for copper, it goes, does it go 2 and 1 in order in the periodic table? Yeah. Okay. So it goes from left to right as the most common charges. So 2 is the most common charge because the first one listed. All right. So once in a while you will run into that problem. Not very often. Okay. But once in a while you might run into that. Okay. This would be the situation that I could think of. All right. Is you're given this reaction here, but you're asked to predict the products. All right. So now, if you're given this reaction and told to predict the products, you have no way to know what charge copper has because it was an element on this side. Okay, so when you make your compounds over here and you go, okay, Cu has to go with S and Cr has to end up by itself, well, how do I know which one to use? They didn't tell me. I go with the most common charge, 2. Bill. Well, because I think this was given to you, was it not? Oh, it was written. Oh, then you go with the most common. Sorry. I didn't realize, sorry, that was written. Yeah. So if they don't tell you, you go with the most common, which for chromium is what, 3 or 2? 3? Okay. Yeah, so Cr2S3. Yeah. Okay, number 6. I've had a few questions on number 6 there on the worksheet. Number 6 looks like this. Okay, we've got hexane, which is C6H14 plus oxygen gas gives carbon dioxide and water. So we had a combustion reaction. 2 special rules for combustion reactions. Balance alphabetically, and the rule of 2. If it's an even number of carbons, we start with a 2. Is this an even number? All right, so I start with 2. 2 times 6 is how many? 12. All right, so I put a 12 over here. Now my carbons are balanced. 2 times 14 is 28. 14 times 2 is 28. So now my hydrogens are balanced. Now I got to look at oxygen. 12 times 2 is 24 oxygens. Plus another 14 more is 38. 19 times 2 is 38. All right, if you start that with an odd number, or sorry, if you start that with a 1, okay, you don't put that 2 in there, you will run into problems because this will end up being 9.5 or something like that, and you can't have half of an, you'll get a decimal here, and you can't have a decimal when you're balancing. All right. Does that make sense? So we got to remember both rules. If they apply and you forget one, okay, you are going to struggle to balance. All right? All right? And for this one, guys, I don't expect that you know that this is hexane. Okay? Remember I said that if the prefix is beyond 10, fuel is fine when you're writing it out in words. Okay? Any other ones giving us trouble?